Nohei City in Aomori Prefecture, running along the coast of Iwate Prefecture. The construction of the Keisanuma Bay Crossing Bridge was a major project aimed at recovery from the devastating Great East Japan Earthquake, which struck the region in 2011. The bridge was designed not only as a means of transportation, but also as a symbol of hope and resilience for the people of Keisanuma. Supported by two towering structures that rise 115 meters above sea level, the Keisanuma Bay Cross Bridge stands as the only bridge on the Sanriku Expressway that spans the sea. With a total length of 1,344 meters, it comprises 680 meters over the water and 664 meters on land. The height from the surface of the sea to the bridge girders measures 32 meters. The overwater section of the bridge takes the form of a cable-stayed bridge, where the bridge girders are suspended by cables fixed on the main towers. This design makes it the largest bridge of its kind in the Tohoku region of Japan. Illuminated at night, the main towers and cables add to the bridge's sleek and elegant appearance, creating a captivating sight for onlookers. The completion of the Keisanuma Bay Crossing Bridge in March 2021 marked a significant milestone in the recovery efforts following the Great East Japan Earthquake. It not only provided a vital link for transportation, but also symbolized the resilience and determination of the residents of Keisanuma. The bridge's nickname, Kanae Ohashi, holds a deeper meaning. The term Kanae is derived from the old name of Keisanuma Bay, Kanae ga ura, while also serving as a verb meaning to realize. This conveys the passionate desire of the local community to achieve their dreams and hopes, even in the face of adversity. Beyond its symbolic significance, the Keisanuma Bay Crossing Bridge offers breathtaking views of the surrounding area. From the bridge, one can witness the scenic beauty of Keisanuma City, the bustling fish market, the majestic Kitakami Mountains, and the vast expanse of the Pacific Ocean in the distance. The panoramic vista serves as a reminder of the natural wonders and resilient spirit of the region. In addition to its aesthetic and symbolic value, the Keisanuma Bay Crossing Bridge serves a practical purpose as a life-saving road. The Sanriku Expressway was meticulously designed to withstand potential tsunamis and ensure the safety of its users. The devastating tsunami triggered by the Great East Japan Earthquake underscored the importance of infrastructure that could resist such natural disasters. With careful engineering and design considerations, the Keisanuma Bay Crossing Bridge was built to withstand the force of tsunami waves, safeguarding the lives of those traveling. The completion of the entire Sanriku Expressway in December 2021 not only connected Sendai City and Hachinohe City, but also facilitated improved transportation and accessibility along the coast of Iwate Prefecture. The expressway has become an essential lifeline for the region, providing faster and more efficient travel options for both residents and visitors. Moreover, it has become a symbol of resilience and recovery, showcasing the determination and spirit of the communities affected by the earthquake and tsunami. The Keisanuma Bay Crossing Bridge stands as an architectural marvel, a symbol of hope, and a testament to human resilience. It serves as a striking visual landmark and a vital transportation link for the Sanriku Expressway. The bridge's construction and completion have not only contributed to the physical recovery of the region, but also provided emotional and psychological support to the people of Keisanuma. The bridge serves as a reminder of their strength and determination to rebuild their lives and realize their dreams, even in the face of immense challenges. As travelers traverse the Keisanuma Bay Crossing Bridge, they are met with a breathtaking view that encapsulates
The Brinkmann-Bodenplatte foundation slab is an innovative and robust solution designed to serve as the foundational base for residential buildings. This foundation system is recognized for its stability, durability, and energy efficiency, catering to a variety of construction methods and building requirements. The foundation slabs are meticulously designed by a team of engineers who customize each slab to align with specific building plans, ensuring that the unique needs of each project are met. The slabs are constructed using high-quality, waterproof concrete W8 25/30, which is is known for its strength and resilience. This concrete is combined with dramix steel fibers and traditional reinforcement methods, a process developed in collaboration with Baykart and a German engineering office. This combination results in a foundation slab that is exceptionally durable, capable of bearing heavy loads while maintaining a relatively thin profile. This structural integrity is a testament to the advanced technology and precise engineering that goes into each Brinkmann-Bodenplatte slab. A key feature of the Brinkmann-Bodenplatte slab is its energy efficiency, particularly its ability to maintain a stable temperature beneath the slab. This is achieved through the incorporation of a frost-resistant wall that is buried below the frost line around the entire slab. This design ensures that the temperature under the slab remains above +9 degrees Celsius, even in harsh winter conditions. This thermal stability not only enhances the energy efficiency of the building, but also allows for cost-saving measures, such as the omission of horizontal insulation under areas like garages, while still applying it under living spaces. To prevent thermal bridging between different areas of the building, a thermal break is installed between the garage and living spaces. The foundation slabs are also designed with varying thicknesses of insulation, tailored to meet different energy efficiency standards, including those of passive houses. One notable option is the heated slab, which integrates a water heating system directly into the slab. This system leverages the high thermal mass of the slab to reduce the energy required to maintain a comfortable indoor temperature, leading to significant energy savings over time. Preparation is crucial to the successful installation of the Brinkmann-Bodenplatte foundation slab. The process begins with a detailed geotechnical analysis provided by the client, which informs decisions regarding soil replacement and sub-base preparation. High-quality sand is selected for the sub-base to ensure ease and effectiveness in compaction, creating a solid foundation for the slab. The slabs are more than just concrete and steel reinforcement. They also include essential infrastructure such as plumbing, utility connections, and drainage systems. The perimeter drain system is particularly important as it removes excess water from around the slab and provides the option to store and reuse this water later. Brinkmann-Bodenplatte prides itself on efficiency, with the capability to construct foundation slabs up to 150 square meters in size within just 5 days. The company offers personalized service, inviting clients to request a free quote by providing their ground floor plans, building cross-sections, and geotechnical reports. In March 2014, the rapid installation of a temporary Bailey-style bridge by the Washington State Department of Transportation, WSDOT, in Thurston County, south of Olympia. This installation was a critical response to a structurally deficient bridge along Little Rock Road, which had been compromised and deemed unsafe for continued use. The Bailey Bridge provided a crucial temporary solution to restore local access while a permanent replacement bridge was planned and constructed. Bailey bridges, known for their modular and portable design, have been widely used in both military and civilian contexts for their efficiency in emergency situations. The installation process for this particular bridge was a collaborative effort between WSDOT and Thurston County crews. These teams worked together seamlessly, combining their expertise and resources to complete the project swiftly and effectively. The time-lapse footage spans 3 days, showing the entire construction process condensed into a brief visual summary. It begins with the initial preparation of the site, including the removal of any debris and the setting up of foundations to support the temporary structure. The modular components of the Bailey Bridge, which are prefabricated and easily assembled, were then transported to the site. Workers can be seen carefully piecing together the bridge, using cranes and other heavy machinery to position the large steel trusses. As the video progresses, it highlights the efficiency and precision of the installation process. Despite the challenging timeline, the crews were able to complete the bridge installation within the planned timeframe, ensuring that local residents and emergency services had restored access across the waterway.
Keisanuma Bay Cross Bridge, also known as Kanae Ohashi Bridge, is a remarkable structure that spans Keisanuma Bay in Japan. It is a significant component of the Sanriku Expressway, a 359-kilometer-long automobile-only road connecting Sendai City in Miyagi Prefecture to Hachi.
FRP composites, but also set a world record for the longest span of its kind. The birth of an innovative project, the Bridge project was born from the need to explore and develop new construction materials that offer superior performance compared to traditional options like steel and concrete. The project was executed by a consortium led by Mostastal Warszawa SA, a company with a long-standing reputation in the construction industry. The consortium also included Promost Consulting T. Siłowski Spółka Jana, responsible for the bridge design, the University Research Center for Functional Materials, which conducted material research, and Rzeszów University of Technology, which handled structural testing. The project was co-funded by Poland's National Center for Research and Development under the Demonstrator Plus program, aimed at supporting innovative research and development initiatives. Why FRP composites? Fiber-reinforced polymer, FRP composites represent a significant advancement in construction materials. Comprising continuous fibers, such as carbon or glass, embedded in a polymer matrix like epoxy resin, these composites offer exceptional strength-to-weight ratios, corrosion resistance, and durability. These properties make FRP composites particularly suitable for bridge construction, where load-bearing capacity and longevity are critical. In the Bridge project, FRP composites were selected to fabricate the main structural elements, such as beams and reinforcements. The use of FRP allowed for the creation of a lightweight yet robust structure, addressing common issues like corrosion and the need for frequent maintenance, which are prevalent in traditional materials. The production process. The production of FRP composite elements for the bridge was a meticulous process. Mostastal Warszawa undertook the fabrication of all composite parts at its facility in Warsaw. The production process involved laying out multiple layers of carbon and glass fiber fabric, which were then infused with epoxy resin using a vacuum-assisted resin transfer molding process. This method ensures that the fibers are thoroughly saturated with resin, producing a high-quality, durable composite material. One of the most challenging tasks in this project was the creation of composite beams, each 22 meters long and weighing 3,700 kilograms. Despite their length, the beams were light enough to simplify transport and installation, reducing overall construction time and costs. The infusion process, which lasted about 8 hours per beam, required precision and control, as any mistake could compromise weeks of work. Structural testing and verification before the bridge could be installed. Extensive testing was carried out to ensure the structural integrity and safety of the FRP components. Rzeszów University of Technology's strength testing laboratory played a crucial role in these assessments. The testing involved simulating various load conditions and monitoring the response of the composite beams to identify potential weaknesses. One of the unique aspects of this testing was the use of acoustic emission methods, conducted by the Warsaw University of Technology, to detect and analyze internal defects in the composite materials. This advanced testing technique allowed for real-time monitoring of the structural behavior under load, providing valuable data for further refinement and validation of the design. Installation and assembly. The installation of the bridge in Blazowa, Rzeszów County, was a testament to the advantages of using FRP composites. The lightweight nature of the beams allowed for a quicker and safer assembly process. The installation of the beams took less than 2 hours, highlighting the efficiency gains compared to traditional materials. The bridge's load-bearing structure was further enhanced by using FRP composite reinforcement bars and a specially formulated lightweight concrete for the deck slab. The final step before commissioning the bridge involved a comprehensive load test to ensure it could handle the expected traffic loads safely. This testing was particularly rigorous due to the innovative nature of the materials used. Over 120 sensors were installed to monitor the bridge's response to loads, including the detection of any micro cracks or material degradation. The bridge was subjected to a static load of 180 tons, far exceeding the design specifications. The results confirmed that the bridge not only met but exceeded its designed load-bearing capacity. The structure demonstrated superior stiffness and strength, and the testing equipment proved inadequate to induce failure, highlighting the robustness of the FRP composite construction. The COM Bridge project stands as a pioneering achievement in the field of bridge construction. It showcases the potential of FRP composites to revolutionize infrastructure by offering a lightweight, durable, and maintenance-free alternative to traditional materials. This project has not only contributed to advancements in material science and engineering, but has also set a new benchmark for future bridge designs worldwide. The successful completion of this project underscores the importance of innovative thinking and collaboration in pushing the boundaries of what is possible in construction. In June 2019, CRL Concrete Repairs Limited successfully completed the supply and installation of 2 identical fiber reinforced polymer FRP composite bridges over watercourses in Ockwells Park for North Yorkshire County Council. These bridges were part of an infrastructure upgrade aimed at enhancing accessibility and durability in the park's pedestrian pathways. FRP composite bridges were chosen for their superior strength-to-weight ratio, corrosion resistance, and low maintenance requirements compared to traditional materials like steel or concrete. This made them an ideal solution for the park's natural environment, where exposure to moisture and varying weather conditions could degrade conventional materials over time. The installation process involved meticulous planning and execution to ensure minimal disruption to the park's ecosystem and visitors. The lightweight nature of FRP allowed for easier transportation and quicker installation, reducing the overall project timeline. Dancy's Pass, a notable and scenic route in the Waitaki district of New Zealand, faced significant disruption when Bridge 66, which carried the Dancy's Pass Road over the Mariwhenua River, was destroyed by flooding in June 2013. This route is crucial not only for local residents and farmers, but also for tourists who frequent the area for its rugged landscapes and historical sites. The loss of Bridge 66 created a pressing need to restore connectivity in this remote area quickly, prompting the Waitaki District Council to seek immediate assistance from the New Zealand Transport Agency, NZTA. The role of the NZ Transport Agency and Downer NZ. Understanding the urgency of the situation, the NZ Transport Agency responded swiftly to the Council's request by commissioning the installation of a temporary Bailey Bridge. Downer NZ, the agency's designated Bailey Bridge Services contractor, was tasked with the installation. Downer NZ has a reputation for effectively managing civil infrastructure projects, especially in challenging environments, making them an ideal choice for this rapid deployment. A Bailey Bridge is a type of portable, prefabricated truss bridge that was developed during World War II for military purposes. Its design allows for rapid assembly without the need for heavy machinery, making it ideal for emergency situations like the one at Dancy's Pass. The modular design of Bailey bridges allows for various configurations and lengths, depending on the requirements of the site, and they can be assembled manually by a small team, which is crucial in remote areas with limited access to resources. The installation of the Bailey Bridge at Dancy's Pass was completed in July 2013, a remarkable achievement considering the remote location and the logistical challenges posed by the environment. The process began with a thorough site assessment to ensure that the bridge could be installed securely and safely over the Mairi-Whenua River. Given the rugged terrain of Dancy's Pass, transporting the bridge components to the site was a challenging task. The components had to be delivered in sections and assembled on-site. Once at the location, the assembly team worked systematically, first constructing the supporting structure and then laying the bridge deck. The modular nature of the Bailey Bridge allowed the team to adjust the bridge's length to match the span of the river, ensuring that it was both functional and stable. The installation was not without its challenges. The team had to work under time constraints, and the weather conditions in Dancy's Pass, known for being unpredictable and harsh, added an additional layer of complexity to the project. Moreover, ensuring that the temporary bridge could withstand potential future flooding was a critical consideration. Engineers had to carefully design and position the bridge to minimize the risk of future damage, taking into account the river's flow and potential for further flooding. The successful installation of the Bailey Bridge restored essential connectivity to the Dancy's Pass Road, allowing residents, tourists, and service vehicles to use the route once more. The temporary bridge also provided the necessary time for the Waitaki District Council to plan and execute a more permanent solution without disrupting the flow of traffic.